Good morning. Hello to everyone, and thank you for listening this contribution. So in this talk, I'd like to present you to discuss a little bit the problem of acceleration and escape of electrons from supernova remnant. You can find details of this work in this paper here that has been recently submitted, and you can find on the archive. So the problem is the following. The observed spectra of electrons and protons at the Earth are quite different. This is something well known since years. Let's say that the proton spectrum is fairly represented by a power law with an index e to minus 2.7. Even if you see in this plot that there are some features, especially the one at the 200, 300 GeV and a possible steepening around 10 TeV. But overall, this spectrum can be described by a power law proportional to e to minus 2.7. The electron spectrum, on the other hand, is quite different and has essentially is composed by two different power laws. One between say 10 GeV and 1 TeV proportional to the energy to minus 3.1, and a steeper spectra proportional to e to minus 3.9 up to 10 TeVs. Notice that the latter point, the red points, are the one detected by Hess, which is a Cherenkov telescope detector. So the different slope with respect to protons is quite striking. Now, since years, one of the explanation, the main explanation to justify this difference was was due to the losses that electrons suffer during the propagation into the galaxy. But two recent works, but even other in the past, but I'm just citing these two works because are most recent, they underlined that propagation into the galaxy following the most recent, let's say, standard model for cosmic ray propagation in the galaxy, they can justify just a little bit of this difference, essentially a steepening of the spectra between 0.1 and 0.3. So accounting for propagation still requires that the spectrum of electrons injected into the galaxy is steeper than the proton one by 0.3 in the energy range between 10 GeV and 1 TeV, and by roughly 1 between 1 TeV and 20 TeV. So this presentation is to propose some, to discuss possible mechanism that can justify this difference. So from the point of view of particle acceleration of protons, we know that supernova remnants since decades have been considered the most probable candidate for the production of cosmic rays. Now, in this talk, we will assume that also electrons are produced by supernova remnants. And if we do this assumption, now the diffusive shock acceleration that we think is the physical mechanism responsible for particle acceleration works in the same way for electrons and protons. The only possible differences can be hidden in two possible mechanisms: the energy losses during the acceleration process, and a possible difference into the injection of particles from scratch into the DSA. Also, it is important to take into account the energy losses that electrons can suffer during the storage time into the supernova remnant. So we will explore these mechanisms. Now, an important point to stress is that the spectrum of accelerated particles at the shock, the instantaneous spectrum, it depends only on instantaneous quantities. So it depends on the sonic and galvanic Mach number, the magnetic field configuration, if there is pre-existing turbulence, magnetic turbulence, and how particles are injected from scratch into the acceleration process. On the other hand, the particles that are released into the galaxy by a single object, by a single supernova remnants, depends on time-integrated quantities. So we have to account for the time evolution of the shock, the energy losses during the acceleration, but also the energy losses during the storage phase when particles are stored inside the supernova remnant, and also how particles escape in time while the remnant is evolving. So we will account for these for all these pieces, making some simplification. For example, first of all, we will account only for type 1a supernovae that evolves in an unperturbed medium, and we will do an analytic calculation. So we will account for the expansion following the Truelove-McKee equations in uniform magnetic field. So you see, those are the equations for the evolution of the shock radius and the shock speed. There is an important assumption that concerns the particle acceleration, namely that protons are accelerated with a constant efficiency up to a phase, which is the adiabatic phase, where the acceleration stops. This is an assumption that is often assumed in the literature, but the real thing, the point is that we assume this because otherwise the spectrum of particles below some energy, below the maximum energy that is reached at the end of the set of Taylor phase, will be much steeper than one measured. So people usually assume that during the adiabatic phase, the efficiency of acceleration drops dramatically. But this is still an open question, why this, if this happened, and if so, why this is happening. Also another approximation, but which is quite a good approximation, is the profile of the velocity of the plasma inside the supernova remnant, which is needed in order to account for the adiabatic losses of particles. So once we know the evolution of the supernova remnant, we have to describe how particles are accelerated. In this work, we do a sort of inverse estimate of the maximum energy. In this sense, usually people estimate the amplification of magnetic field. From this, it is inferred the maximum energy of particles. We are doing the opposite. Namely, we assume some function for the evolution of magnetic field, for the evolution of maximum energy in time, which is a simple power law proportional to T to minus delta, where the two free parameters are Pm, which is the maximum absolute momentum reached at the beginning of the set of phase, and delta is the power law index, which is an arbitrary parameter. Then we assume that the maximum energy is determined by equating the age of the remnant with the acceleration time, which is connected to the diffusion coefficient, which is in turn connected to the turbulent magnetic field. Now, knowing the maximum energy, we can infer the turbulent magnetic field, and from this magnetic field, which is connected to the power spectrum F by this equation, we can finally infer the maximum energy of electrons that are regulated by energy losses. So we first start with the maximum energy of protons, we determine the magnetic field, then we calculate the energy losses of electrons, and equating the acceleration time of electrons with the minimum between the age of the remnant and the energy loss time, we determine the maximum energy of electrons. So this is the way we implement the calculation of the maximum energy. Once this is done, we determine also define the escaping time of particles, which is the moment when the maximum energy at the shock is reaching some fixed momentum P. So it's enough to invert this equation, which is expressing the maximum energy of protons. This is namely the time when particles with some momentum P are allowed to escape from the remnant. So in this plot on the right side, I'm showing the behavior of maximum energy of protons with dashed lines and electrons with solid lines for different values of this parameter delta. And you see this is as a function of time divided by the set of time. And you see that around 100 t set of it begins the adiabatic phase. So essentially here we assume that the acceleration stops and particles are released into the interstellar medium. Now, as soon as the maximum energy of electrons remains below the maximum energy of protons, they are confined inside the remnant. On the contrary, when these two quantities become equal, also electrons start to escape from the remnant. Look, for example, the difference between the blue lines that are being computed using delta equal 1. In this case, the maximum energy of electrons are always smaller than the proton one. While for delta equal 2 and equal 3, you see that after few times the set of time, the maximum energy of electrons due to losses is becoming smaller than the maximum energy of protons. This means that losses are no more important, and also electrons can start escaping from the remnant. Okay. So then, after calculating the spectrum at the shock, we also calculate the spectrum inside the supernova remnant, accounting for radiative losses that affect electrons, adiabatic losses that affect electrons, protons, but also magnetic field. So the magnetic field, again, is amplified at the shock, is compressed by cosmic rays, is compressed at the shock, and then evolves, losing energy because of adiabatic expansion. In those two plots, on the left side, you see the evolution of magnetic field inside remnant for some fixed time. So t equal the set of tail, set of time, the 10 times this time and 50 times this time. And on the right side, instead, you see the maximum energy of electrons inside the remnant. This plot is just to show that because of adiabatic losses are changing in time, the maximum energy of electrons is not always located close to the shock here, but depending on the evolution phase of the remnant, it can be located even inside. So you see that there are the behavior of the maximum energy as a function of the radius is not constant. Okay, then again we calculate the distribution function of particles, protons, and electrons inside the remnant. And in this plot, I'm showing which is the distribution at some fixed momentum, two momenta, 10 GeV and 10 TeV, at the moment when those particles are escaping, namely at the escaping time of these particles. This plot is meant to show that, again, the bulk of particles are not always located close to the shock, but sometimes, because of the presence of losses, they can be located in the innermost side of the remnant. You see, for example, the 10 TeV line is showing a peak here, while at 10 GeV, the 10 GeV line has a peak close to the shock. Okay, so this is the model, and now we have to calculate the final spectrum that is ejected into the galaxy. This is composed by two different terms. One is the particles that are located inside the remnant, which is this term here. So the contribution from the downstream. This is nothing but the spatial integral from 0 up to the escaping radius of particles of the distribution function inside the remnant. Then there is an additional contribution coming from particles located inside the cosmic ray precursor. And also this can be relevant, especially for the highest energy particles. You see on the right side a plot showing the downstream contribution and the upstream and the precursor contribution. Look at the solid, at the blue lines. So the solid line is the total integrated spectrum, while the dashed line is the contribution from the precursor, and the dotted line is the contribution from the interior of the remnant. You see that in general, the contribution from the precursor is always negligible, but the maximum, the energy close to the maximum possible energy. The red line, on the contrary, they represent what is happening if we assume that particles are all escaping at the end of the set of Taylor phase. Namely, this is another assumption that it is often assumed in the literature, namely that particles are stored inside the remnant until the remnant literally dies. While we are assuming that particles are escaping at all times from the shock as soon as their energy is larger than the maximum energy at the shock at that time. You see that with the red lines present a spectrum which is much steeper, and this is just due to the fact that they are losing much more energy due to adiabatic losses, because they stay inside the remnant for a longer time. Okay, now let me show you some result. So this is a result for the proton and the electron spectrum finally injected into the galaxy by a single supernova remnant, changing essentially two parameters: the maximum energy PM, which is equal to 10 to 5, so 100 TeV, and 1 PV on the right side. And the other parameter is delta, which is assumed to be equal to 1 or 2. So on the top panels, it is equal to 1. Bottom panels, it is equal to 2. The blue lines are showing the proton spectra, while the orange lines are showing the electron spectra. You see that we can conclude that the electron spectrum, it is different from the proton one only if the maximum energy PM is of the order of 1 PV. Look at this plot here. While if it is smaller than 100 TeV, the two spectra are only slightly different. And the other important parameter is delta. If delta it's smaller, it's of the order 1 or even smaller, the electron spectrum, it is more different because the magnetic field is amplified for a longer time. While you see on the bottom left panel, if you assume delta equal to and Pmax equal to 100 TeV, the two spectra of electrons and protons are essentially equals. Now, what we can conclude from these plots is that changing parameters in a reasonable range of values, the difference between electrons and protons can be at most down to 1 TeV. For energy smaller than 1 TeV, it is very difficult to produce a different spectra. One has to assume unreasonable large level of magnetic field amplification. No, those results have been already also obtained with the different techniques by these other two papers, one by Christopher and collaborators, the other by Bros and collaborators. So on top of this, we have also analyzed other two mechanisms. One is the possibility that the magnetic field amplification is occurring also downstream of the shock due to MHD dynamos. So if the shock is propagating to an uniform medium, the shock rippling is producing turbulence that is able to amplify the magnetic field in the downstream. Now, this amplification does not affect the maximum energy reached at the shock, because it's not amplifying also upstream, but it will affect the evolution of particles of electrons in the downstream. On the right side, you see a plot showing again a difference between the proton spectrum and the electron spectrum. For this mechanism, we have done a very simple assumption. We assume that some fraction psi b of the incoming of the energy flux of the shock is converted into magnetic turbulence, again in the downstream. So, and this psi b should be of the order of few percent. And you see here on the left, on the right plot, changing xi b from 0 up to 10%, how the different lines are producing a change in the slope at lower and lower energy. But even assuming xi b up to 10%, which is already quite unreasonable, the spectra of electrons is changing above 100 GeV, so never below that. Another interesting thing of these mechanisms is the fact that there is an additional, the additional contribution coming from the precursor is not affected by losses due to MHD amplification. And so particle electrons that are escaping from the precursor are not affected, and they produce a flattening of the spectrum above let's say, something of the order of 10 TeV. Okay, so the last mechanism that we have been analyzed is now that we know that the amplification of magnetic field is unable to affect the electrons spectrum below a TeV, of something of the order of 1 TeV. Let's assume that there is another mechanism, namely the possibility that electrons are injected inside the diffusive shock acceleration in a different way with respect to protons. And we assume this equation, that the ratio between electrons and protons is proportional to the velocity of the shock to some power law, negative power law. So essentially we are assuming that our electrons are more easily injected into the shock acceleration when the shock speed is lower. This Qk is a free parameter. Now the shock speed can be related to the energy of particles through the escaping time, and so through this equation here. And so we can connect the ratio between electrons and protons at each single momentum of the spectrum which is injected into the galaxy to these two quantities, Qk and delta. And for a different spectrum, and from a delta S equals 0.3, which is the one measured, the difference between proton and electron inferred from data, this implies that Q has to be something of the order of 1, assuming that delta is equal is of the order of 2, 3. I forgot to mention that this delta is indeed a free parameter, but we have used this model to fit the gamma ray emission from several supernova remnant, and usually we infer a delta of the order of 2, 3. So this is why the reason why we are taking this number. So again, assuming delta between 2 and 3, we infer a Qk between 1 and 1.5. So this means that the injection of electrons should be inversely proportional to the shock speed. And this is our conclusion, that in order to explain the spectrum at the Earth, the electron spectrum at the Earth, assuming that this is produced by supernova remnant, we have to assume that the one possibility, we think the only reasonable possibility, is to inject electrons into the shock in a way inversely proportional to the shock speed. Now, is this compatible with what we know about shock acceleration? Before jumping to the last conclusion, let me just show you the entire electron spectrum, assuming, including now all the effects. So the self-generated magnetic field, the magnetic field amplified by MHD, by dynamos, turbulent dynamos, plus the time-dependent injection of electrons. And this is the final plot, where again I'm showing the proton spectrum with blue lines and the electron spectrum with orange lines. And there are a few things to comment. So below something of the order 1 GeV, there is an hardening, essentially due to the fact that here, this energy, the acceleration is stopped. So below this energy, essentially the spectrum that we see, it reflects the spectrum that is accelerated at the shock. It is not time integrated. Above this energy, so between few GeVs and 1 TeV, the spectrum is steeper because of the time-dependent injection, with injection of electrons inversely proportional to the shock speed. Between 1 TeV and 10 TeV, the spectrum is steepens because of energy losses due to synchrotron losses. And notice that in this case, I mean, using parameters suitable in order to fit the electron spectrum at the Earth, the self-generated magnetic field is not enough to account for the correct break observed in the electron spectrum. We also have to assume some level of turbulent amplification in the downstream, because this is producing a much sharper cutoff. Finally, above 10 GeV or so, we see a hardening of the spectrum due to electrons that are escaping from the precursor of the shock. So this is essentially the final exercise. Now let me just finish this talk mentioning a couple of evidences that are supporting the idea that electrons are injected inversely proportional to the shock speed. So the first one is coming from Balmer lines. For collision and shock observed in Balmer lines, it is possible to infer the electron to proton temperature just behind the shock. Okay, this has been done by several papers, especially by Van Adelberg et al. And so you see in this plot on the right, data showing the temperature electrons over protons with respect to the shock speed. Okay, and in this paper they inferred a behavior which is inversely proportional to the shock speed to the square. Now you see that this is quite the case up to, let's say, 200 to 1,000 kilometers per second. Above this energy, above this velocity, this line does not seem to be very good. But in our context, we are only interested in shock speed below roughly 2,000 kilometers per second, simply because electrons are escaping from the remnant only for shock speed below this value. Above that, they are confined inside the remnant, so we are not interested in that. So again, the electrons over protons ratio is proportional to the shock speed, now to the -2. Now, because of the proton temperature is proportional to the shock speed to the square, this observation implies that the electron temperature is constant, does not change, changing the shock speed. And from data, they inferred that the temperature of the electron is of the order of 0.3 keV. And this should be energy transferred from protons to electrons by some mechanism. Okay, so this is the first piece of information. Now, the second piece of information is coming from peak simulations, especially, well, from this work by Arbutin and Zekovic. So they, using peak simulation, they were able to infer which is the amount of electrons and protons that are injected into the SA. So in general, one important parameter that people use to distinguish between thermal and non-thermal particles at the shock is this P injection. This is the momentum where the thermal spectrum ends and the non-thermal tail begins. And usually this is assumed to be xi times the thermal momentum of the thermal distribution. Now, Arbutin and the total amount of particles that are contained inside the non-thermal tail are expressed by this number, eta E, which is a function only of this parameter xi. Now, Arbutin and Zekovic were able to infer that these two numbers are essentially the same for both protons and electrons, in spite of the fact that electrons, in order to be injected into the SA, they should be pre-accelerated by some mechanism which is not the SA. But in spite of this, they found that these two numbers are equal are essentially equal, of the same order. Now, if we now evaluate the ratio between electrons and protons, this ratio, KEP, is given by the number of electrons and the number of protons injected inside the non-thermal tail times the ratio of P injection for electrons and protons to the power of the slope at that energy, which is the slope which is connected to the compression ratio at the shock, very close to the shock. So this is called the subshock compression ratio. So, and this is, at the end, this is proportional just to the velocity of the shock to -2 times 3/2 r sub -1. This means that for subshock ratio, compression ratio, which is of the order 4, KEP turns out to be proportional to the velocity of the shock to -1. So this is exactly what we need in order to explain the electrons, the difference between electrons and proton spectrum that we observe at the Earth. So this seems to close the circle, justifying our finding of this inverse proportionality. But there is at least one caveat. This peak simulation performed by Arbutin and Zekovic are limited to relativistic electrons and only for the ratio, mass ratio between protons and electrons smaller than 100. So in my opinion, this needs to be further tested. Okay, I'm coming to my conclusions. So we have discussed the fact that cosmic ray electron spectra is steeper than the proton one by 0.4 in the range between 10 GeV and 1 TeV, and by 1.2 in the range between 1 and 10 TeV. Losses during propagation inside the galaxy cannot account for these differences. So the difference should be due to either the acceleration or to the release process that occurs at the sources. So in this paper we have assumed that both protons and electrons are accelerated at supernova remnant shocks, and we investigated two possible mechanisms that can produce this steepening. Synchrotron losses due to amplified magnetic field, either amplified by cosmic rays or amplified by MHD dynamos, and a time-dependent injection of electrons. The results are that synchrotron losses can steep the spectrum only above a TeV, roughly TeV, while time-dependent injection can further steep the spectrum by 0.3 down to GeV energy if the electron to proton ratio is proportional to the shock speed to the -1. And we discussed some observational evidences supporting this inverse proportionality, even if it remains to be understood why this is happening, which is the physical mechanism behind this behavior of electron injection. That's all from my side. Thanks a lot for listening, and I hope to see you in phase very soon. Goodbye.